Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 4, Lecture 3 of Dynamic Atomic Force Microscopy Methods. In the last class, we summarized the different methods available that allow one to convert the observables in frequency-modulated AFM, which is a frequency shift as a function of Z, into quantitative estimates of the conservative tip-sample interaction forces between the tip and the sample. We talked about the fact that there are methods that assume small oscillation amplitudes. There are methods that assume large oscillation amplitudes, but lately there's been an emerging consensus on trying to use a unified approach which does not require an assumption on the oscillation amplitude, such as the formula given by Sater and Jarvis, or the matrix method that's been proposed by Gazebel's group. So what's shown out here, for example, is the formula that allows one to convert the relative frequency shift omega into the tip sample interaction force at the location of the lower turnaround point, or DLTP. Now, today's lecture, we're going to take a step back from the theory that we've been developing to talk a little bit about some experimental aspects of, FM-AFM. In particular, we've already talked about the phase lock loops and the different ways in which you actually implement the hardware and electronics needed for this. We haven't talked about the hardware and electronics in much detail, but hopefully in week 2 we went over some of the broad outlines of it. And the appendix of this lecture, we've tried to introduce again some more information on phase lock loops, and you're welcome to look at those. But what we're going to do is when one tries to look at applying frequency modulated AFM, one has the choice of using normal cantilevers or some other kind of probes. So it's useful to start thinking about what would be the ideal kind of probe to reconstruct interaction forces between the tip and the sample. Now, it's bound to be important for the kind of measurements we've already been talking about that there be very high stability, or that the probe be very stable from the point of view of for example, that its frequency shifts not change significantly due to temperature changes or humidity changes and so on. This becomes very important because we're going to be tracking frequency shifts. We want the frequency to shift only because of tip sample interaction forces and not because of any other external effect. So that's what we mean by stability. The second important thing is that once we make sure that the frequency shift is due to the tip sample interaction forces alone, we want to measure the frequency shift accurately, and that's where the hardware and the electronics comes in. And lastly, we would like to choose a very stiff cantilever. Why would we want to choose that? And the answer to it goes back to part 1 of this course, where we did static methods, and you'll recall that when one looks at the tip sample interaction force curve and looks at the intersection of that with a straight line with the slope corresponding to the spring constant of the cantilever, the intersection points really allow us to look at how d star, which is the equilibrium tip sample gap, changes as a function of z. And you recall that if the spring constant of the cantilever is larger than the gradient of tip sample interaction forces in the entire range, in that case, at every z distance, there's going to be just one intersection between the constant slope stiffness line of the cantilever and the tip sample interaction force, meaning that there would be basically no pull-in or snap-out kind of phenomena. Whereas when we choose a softer cantilever, which is shallower slope, you can imagine that at some z distances, that shallower slope would intersect the interaction force curve at multiple points, allowing for multiple states where the tip is stuck or pulled away from the sample to exist. So all these are 3 basic requirements for needing to do frequency modulated AFM-based spectroscopy. Now, there are many other needs also which we can bring in, but these 3 can be regarded as some of the important ones. The ones that we're not talking about here are the whole notion of noise. We're not talking about the issue of noise from phase detector noise to laser noise to many different noises that actually influence this. And some of the references I've put at the end of this lecture will give you more of a flavor for all the details of those processes. We're also not talking a whole lot about Q factors and how operating conditions need to be optimized for frequency modulated AFM. So this is going to be a broad overview of some experimental details of FM, AFM, especially in regards to spectroscopy. So one can do this with normal cantilevers, right? With silicon cantilevers that are sufficiently stiff, and you can still use the optical detection method to do it. However, from the early days of FM, AFM, it became apparent that there would be considerable advantages if we could change the kind of probe that were being used for doing force spectroscopy. And that's when the idea of the quartz tuning fork came up. So in this particular lecture, we're just going to focus on this alternate probe, which is a quartz tuning fork. Keeping in mind the regular stiff cantilever with a laser photodiode, we've already talked about how that works, so we'll focus on this particular method. Now, quartz tuning forks can be found in everywhere around us. They're there in most watches and chronometers, for example. And what's shown out here is a typical quartz tuning fork that sits inside a watch, for example. It's depending on the size, it's got a little capsule around it, and it's actually packed in low pressure. And so if you pop open the container, you see the tuning fork inside it. What's interesting about tuning forks is their natural frequencies have been designed to be 2 to the n integer power. So a very common rendition of this is 2 to the 15, which gives you about a resonance frequency of about 32 kilohertz. Which makes this tuning forks ideal as being as clocks to be integrated into microprocessors and electronic circuits and so on. The big advantage, of course, is cost. It turns out that these things can be fairly cheap. You can buy them, for 25 cents if needed. And so it's very interesting to look at the possibility of using quartz tuning forks for doing frequency modulated AFM. It is probably useful to step back and talk a little bit about quartz. What is it? The piezoelectric properties of quartz have been known for more than a century now. It is a piezoelectric material, but a highly anisotropic piezoelectric material. And there are many planes of symmetry. Many of you or some of you may know how just in elastic materials you could have anisotropies in different directions with different elastic constants. In the case of piezoelectric materials, you've got an electric response and you've got a mechanical response. And so the symmetry groups of piezoelectric materials can become considerably more complicated. And as a result, when one takes pure quartz, which is basically a form of silicon oxide, there are many faces in which you can cut a quartz crystal. What I've shown on the top left are many such cuts, and every cut is used for a different category of device. The cut which results in the tuning fork is shown there. The specific cut that results in the tuning fork is also shown there. But once these cuts are made, we expect a certain orientation of electromechanical properties of the resonator. Now, what's really interesting about quartz tuning fork is that its piezoelectric properties endowed with 2 important properties. The first is that when you apply voltage to it, it induces strain and mechanical deformation in the probe. The second thing is it's piezoelectric, so mechanical deformation generates electric charge across electrodes as well, which you can detect with a current amplifier or a charge amplifier. As a result, what's really nice about these probes is that you can, in principle, operate them by purely electrical actuation, and you can detect frequency shifts purely by looking at the electrical signal output from these probes. That's one big advantage. The second advantage, which is a very useful property of quartz, is that the resonance frequencies of quartz oscillators as a function of temperatures are known to be extremely stable. This is a major reason for wanting to use quartz-based tuning forks. So what's shown out here is an example of how the frequency shift for a tuning fork versus a silicon cantilever change as a function of temperature. And one notices that when you're talking about silicon cantilevers, the change occurs rapidly. And when you're talking about silicon cantilevers or quartz-based tuning forks, they're very robust, very stable resonance frequencies. Now, you may well ask the question, why are we going to be concerned about temperature changes and their effects on resonance frequencies? Now, like I mentioned to you, most AFM setups, the temperature is not constant. And especially when one is trying to do experiments where you're bringing the temperature down, you're doing a cryogenic non-contact AFM system, implementation. In all these cases, you have very high thermal gradients, basically, and you can expect to see, even in very well-designed systems, some variation in temperatures, some drift in temperatures that actually happen. Because at the end of the day, you might actually even have a temperature controller set inside the AFM system, but it doesn't really control the temperature at the probe itself, at the probe tip itself, which is where you want to control it. As a result, there are going to be temperature changes, and temperature changes, if they also cause a change in frequency, is going to be of significant problem as far as stability of AFM is concerned. So this is another important reason why quartz tuning forks turn out to be very successful and useful in AFM. The other thing about quartz tuning forks is that once one does the appropriate cut from the quartz crystal and makes a tuning fork with two arms and a base, two tines and a base, one has to set up electrodes. Every piezoelectric material needs to have electrodes around them. The electrode configuration for tuning forks is very interesting and leads to some very interesting properties. It's very cleverly designed electrode designs, but specifically what ends up happening is the electrode geometry effectively chooses the vibrational mode that one excites in the tuning fork. It also effectively chooses what kind of motion one is actually sensing. So for example, in this electrode configuration shown out here, you have arm 1 and arm 2. The black is one continuous electrode, and the gray shaded is another electrode. What one notices is the electrodes actually span both arms. They go from arm 1 to arm 2, and both electrodes do. But if you were to apply a voltage across these two electrodes, an alternating voltage, what you would see, based on the configuration that I've shown out here, that the polarization of the two arms would happen in opposite directions at any given instant, which would lead to a motion which causes an out-of-phase motion to occur. So, in other words, when let's say when the black electrode is positive and the gray electrode is negative, you see the patterns that would be generated in the cross sections of the two arms, shown on the bottom right. The red refers to positive voltage, blue refers to negative voltage, and you can see the patterns are reversed, which causes a net relative motion of the two arms, a net force or expansion in opposite directions. And so the electrode design itself naturally prefers the out-of-phase oscillation mode. There is another mode, which is the in-phase oscillation mode, which can be excited and is best excited by inertially exciting such a quartz tuning fork. So here's an example of what happens when you break out one of these tuning forks out of the cylindrical capsule in which it's kept inside. This is an example from a thesis in the physics department at Purdue from Ron Reifenberger's group. What's shown on the y-axis in this graph is the current output from the tuning fork. Remember, as the probe oscillates, it's also going to generate a voltage which you can measure, and you can measure it in the form of a current as well. So the current's been measured along the y-axis. The frequency at which you're electrically exciting it is along the x-axis. One finds that when one measures this response in in vacuum, you get a very high Q factor, but as soon as it is brought out into the ambient conditions, the Q factor reduces and the resonance frequency actually drops as well a little bit due to the added mass of the surrounding air molecules and so on. But nonetheless, when one looks at Q factors of these quartz crystal tuning forks, they're extremely high. You can expect to see, Q factors of the order of 10,000 sometimes. So this is a fairly useful thing to have for when one does FM, AFM, high Q factors are useful because they allow you to track better the frequency shifts. The other thing I want to bring to your attention is the value of the stiffness. Now, in this particular case, the stiffness has been calculated by looking at the dimensions of the tuning fork and the elastic modulus and using beam theory as discussed in part 1 of the class. And it's very normal to have tuning forks with stiffnesses of the order of 1,000 to 10,000 Newton per meter. They're extremely stiff. So it's, you can be pretty sure that the snap-in and pull-out phenomenon is not going to happen. And it's a high Q factor, so it allows you to track frequency shifts a little better. So all these are pretty good advantages. I'm going to, again, talk about one little experimental detail. When one uses a tuning fork in the configuration when one electrically excites it and electrically measures its response, because the response is then going to be measured in terms of the current coming out of the probe as a function of the drive frequency. So this is a tuning curve shown on the left. There's a resonance at which current increases, and then there is right after the resonance peak, there's a little bit of a dip, which is an anti-resonance. So this curve, when you look at it, doesn't look like the standard curve of an externally excited oscillator. And when one deals with electrical circuits, such as the one needed to excite and measure from a tuning fork, one needs to be very careful about parasitic capacitance. In other words, what's shown on the top right is an equivalent circuit diagram of the system. You have the RLC, the resistance, impedance, and capacitance corresponding to the tuning fork, but there's going to be inevitably a parasitic capacitance that comes and shunts some of this the circuit. And as a result, you can show, and the details are shown in the appendix as well as here, that this kind of the parasitic capacitance is pretty important to understand why you get the anti-resonance behavior in these tuning curves. And then, of course, once you understand the source of this anti-resonance, you can correct for it with some clever analog circuit design, as explained in the appendix and shown in the bottom left. So these are some important things to keep in mind as one tries to implement this in a purely electrical readout form for doing FM, AFM. Now, if we're going to be reading out the current as our output, we need to calibrate it, because at the end of the day, when we do an approach curve, we're using the Sater-Jarvis formula or the matrix method to get interaction forces. In either case, we need to know what the oscillation amplitude is. So one needs to calibrate the oscillation amplitudes. One good way of doing it with tuning fork oscillators is to use a fiber optic interferometer, which is a thin probe that actually comes down. And what it basically does is it uses the fact that part of the incoming beam is going to reflect off the end of the fiber, and then part of it goes through, reflects off the surface, and goes back in to the fiber. And the difference between these two signals the interference can be used to judge what is the displacement of the surface. There are many details about these kind of proximal probes, which I can't go into right now. But the key point here is, at some point, one needs to be able to map the amplitude as measured in the current signal to the actual amplitude in nanometers. And this is a frequently used method to try and really calibrate the signal, the measured signal. Now, at the end of the day, one also needs to take this tuning fork and attach a tip to it. There are many ways of doing it. One can deal with many kinds of tips, and if one is interested in having AFM tips in particular, you can actually, as shown on the bottom left, you can actually take an AFM cantilever, break it off, and actually attach it to one of the tines. The configuration showed on the left is what I would call both tines or both arms being free. This is a configuration used quite often by a number of groups, where both the arms of the tuning fork are allowed to vibrate. On the other hand, on the right-hand side, I've shown you work that's been driven by Giesebel's group in Germany, which basically is now available commercially. It's called the Q+ sensor, where the tuning fork is set up in a way where it's bound to a ceramic chip, where one tine is bound and the other tine is allowed to oscillate. So one truly recovers a single cantilever quartz, a quartz sensor, a quartz cantilever beam, basically. And then one can drive it with electrically with one channel, and one can measure the piezoelectric response in the other channel. So how would one use this kind of a tuning fork setup to actually measure interaction forces? Well, one would set up a circuit roughly along the lines as shown here. You can operate this probe both in amplitude modulation, or you can use it in frequency modulation as well. What I've shown here is one particular implementation where the phase lock loop has been put into place, and the drive frequency is now going to change to keep the natural to track the changing frequency of the probe due to the tip sample interactions. This particular diagram here does not at the moment show a control of the oscillation amplitude, but this is an experiment that was performed in what's called the constant excitation mode with a phase lock loop as one approaches the sample. So the idea then would be to approach the sample and measure frequency shift in amplitude change as a function of Z. And that data are shown here for a tungsten tip approaching a freshly cleaved graphite surface in air. On the left-hand side on the top, you see how the amplitude changes for different values of initial amplitudes or unconstrained amplitudes of the probe tip. On the right-hand side, you see the corresponding frequency shifts. And then what you see at the very bottom is using the Sater-Jarvis formulas to reconstruct the tip sample interaction potential in all these three cases that's shown. What lends confidence to the method is the fact that the data were connected for three different free amplitudes or three different unconstrained oscillation amplitudes. At the end of the day, the interaction forces that you get out of each of those three curves, they still fall on the same curve basically as shown on the very bottom here. So this is how one would actually implement with the tuning fork the approach or the reconstruction of tip sample interaction forces. Now, as I said, we've discussed in this class just one such probe. As far as normal AFM cantilevers are concerned, the methods for doing them have already been discussed before, and we will not be discussing those special needs any more in this particular part of the class. I do want to emphasize that a key thing and a key issue in frequency modulated AFM is the hardware and electronics. We will not have too much time to go into the hardware and electronics, but the appendix has more information on some more details of phase lock loops and feedback loops that are used in FM AFM for those of you who are interested to pursue such a line of investigation. Thank you very much.